Sorry. Right. The other thing is that, as always, I'm supposed to remind you every class, apparently, but fine. We receive lots of pressure on that, so the university seems to care for it, okay? So part of the issue is that they do not want to have situations in which the class is entirely moved as a recorded class, okay? So if you're here, you're listening to me, also go to your agenda and record your presence, even though it's not physical presence. That's for the purpose I told you, I think. All right, so the oppositions were between reduced form and structural VARs, and between constrained and unconstrained VARs. The unconstrained VARs, they are good, they are beautiful, because you can actually deal with them as systems of regressions in which you estimate each regression separately from the others just by using OLS. So if you have a reduced form VAR and there are no constraints, essentially in terms of estimation, there is nothing more to know than econometrics 1. So you do not even need econometrics 2 to deal with them in the estimation stage. If instead you have a VAR, even the simpler VAR, so the reduced form VAR, but there are constraints, meaning that some of the coefficients have been set to 0, or some of the coefficients have been set to values that you know for some reason ex ante, then unfortunately you cannot estimate the VAR by OLS equation by equation, and you have to apply what we call methods for system estimation. It means that you cannot break down the system of regressions into a stack of regressions, but all of them jointly, they have to be taken care of when it comes to estimation. Practically, there is a method of estimation which is appropriate to such system of regressions, which is called GLS, where G stands for generalized, so it's generalized least squares. I don't know if you cover GLS in Econometrics 1, you should, but all right. But in any case, it's not so important, because it turns out that if you apply maximum likelihood estimation, which we spoke about already, to a system of regressions, you automatically get GLS. So if you always do maximum likelihood, that's okay. Now, in our case, practically what will happen is that if there are restrictions, EViews, or other software packages you can get access to, they automatically apply maximum likelihood, and therefore they do GLS. The other opposition, which is what I also will cover today, is between structural and reduced form VARs. So reduced form VARs are in the way that you see here in the slide right now, in front of your eyes. So it is when you have YT on the left-hand side, and then on the right-hand side, you have legs of Y and a bunch of coefficients. So A0, A1, A2, blah, 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 AP. And reduced form VARs, they have two advantages. If there are no constraints, then you can estimate them by OLS, as I already said. And second, they are ready for forecasting applications, in the sense that at time t, you will know, say, the past Ys. You will not know the shocks, because the shocks, they are random, so you will know that they have zero expectation. So if I provide information at time t on the variables on the right-hand side, and if you have estimated the coefficients, you're ready to produce a forecast for the left-hand side. So that's the natural way in which the models are written when you care for predicting the future. On the contrary, structural VARs, they are not in a ready shape for forecasting, and their feature is given by the fact that this is one example, but basically it embodies all the properties that I want to stress. A structural VAR is such that in each equation, you have contemporaneous effects. So you see that xt on the left-hand side depends on zt on the right-hand side contemporaneously, meaning the time index is the same on the left and on the right. And the coefficient mediating such dependence, contemporaneous dependence, is called the B12. In the second equation, zt on the left-hand side depends contemporaneously on xt on the right-hand side, and the coefficient mediating such dependence is given by B21. So in a reduced form VAR, it's called reduced form because there is no contemporaneous dependence, and any contemporaneous relationship between the y variables on the left-hand side has to go through, let me show you, has to go through the shocks UT. And in fact, as we saw, the shocks UT, they may have a full covariance matrix, meaning that they can be contemporaneously related. But it's the shocks which are related, not the variables yt in an explicit form. If instead you're looking at the structural VAR, like in this example, then the contemporaneous relationship, they are outright relationship, and they are visible in the very form in which you write down the regressions. Now, to avoid a problem of identification, so not knowing where the contemporaneous dependencies come from, whether from the regressions or from the shocks, it is classical, it is typical to assume that the shocks to a structural VAR, the epsilons, there is a noise, but it's not you guys, all right? The epsilons that you see here, they are uncorrelated. So the covariance between epsilon tx and epsilon tz is assumed to be equal to 0. Notice that you do not have to, but it's a healthy measure, because otherwise it will be difficult to disentangle how much contemporaneous correlations come from the B12 and B21 coefficients, and how much it may come from the residual. So they better be uncorrelated. Last time, I actually spoke about how you go from a structural VAR to a reduced form VAR. And if you want to see the algebra step by step, because now you're looking at a slide, which is okay in terms of grasping the intuition, is not so okay if you want to, look at the algebra for real. I have posted a recorded lecture in which I use the classical, say, electronic whiteboard to do the algebra in front of your eyes. But it's optional, meaning that in the exam, I will not test knowledge of the algebra. And in general, I was not testing the knowledge of the algebra even before COVID. So it's not related to the form of the exam. But some of you may actually want to take a look. All right. So quickly, let's review it. So first step, I wrote down our structural VAR in matrix format. So instead of writing the two regressions and stacking them on top of each other, I'm using vector and matrices, which gives an equivalent result. The only thing is that I have to give names to the matrices and vectors. So I call the matrix, which collects the contemporaneous effects, the contemporaneous coefficients, I call it B. I call the vector stacking x and z, y. I call the vector of intercepts gamma 0. I collect the gamma 1, 1, gamma 1, 2, and so forth coefficients inside the matrix gamma 1. Obviously, on the right-hand side, I got legs of x and z, so I've got yt minus 1, and finally I collect the two structural shocks, epsilon tx and epsilon tz, into a random vector called epsilon t, which is a vector of white noise. It can be characterized as a multivariate white noise if needed. So in compact form, your VAR, structural VAR, can be written in the way that you see here. Now, let's spend one moment to contemplate the structure of the matrix B. B is a full matrix. It's the matrix of contemporaneous effects, and it plays a special role because it pre-multiplies yt on the left-hand side. So this makes this model, if you want to see that as a regression, as an autoregression, it makes it weird. Because usually in regressions, included autoregressions, you have y alone on the left-hand side, explained by other stuff. In this case, explained by its own past. But this is not the case here, because you have a matrix which actually takes weighted linear combinations of yt on the left-hand side. So this seems to be a problem. The matrix B is a strange matrix because it has ones on the main diagonal. The reason is that you still want to associate each of the regressions, each of the equations of the VAR with one of the variables. So it is, for instance, here, in this case, up here, xt has a 1 in front of it, right? Because this is the regression for xt, and so xt goes alone on the left-hand side. This is reflected by the presence of the 1 in the first position of the main diagonal of B. And same for the second regression, there is a 1 in front of zt. It's invisible, but there is a 1, and is reflected by the second one on the main diagonal of B. So it's a full matrix, but with ones on the main diagonal for, we say, normalization purposes. So it will always be like that. Now, the content, the true information of the matrix B comes from what happens outside the main diagonal. So from the coefficients B1, 2 and B2, 1. If these guys are here, and so potentially they can be estimated to be different from 0, then it means that in principle you are accepting the presence of contemporaneous effects, which makes the VAR a structural VAR. Now, if I leave the VAR in this form, I will tell you also exactly why, but it's trouble, because you will not be able to apply OLS, you will not be able to apply econometrics 1, so simple estimation, and the reason is the presence of B on the left-hand side, as I was saying, because this cannot even be read as a regression. So wonderful idea, that's quite natural. Well, but maybe I can get rid of B on the left-hand side and have YT alone left on the left-hand side. How can I do that? Well, if B, being a square matrix, were invertible, you know that if you pre-multiply both the left-hand side and the right-hand side by the inverse of B, you will get rid of it, because the inverse of B times B is the identity matrix, which becomes invisible. And then you will have the matrix B inverse pre-multiplying everything on the right-hand side. And that's exactly what we did, right? Now, the only caution, say, is that on the right-hand side, I will lose the ability to distinguish between the elements of B and the elements of gamma naught, the elements of gamma 1, and the elements of the vector epsilon. And so I want to create new names. I want to give new labels to the same objects that we had before. So we call B inverse gamma naught A naught, vector of constants. We call B inverse gamma 1 A1. And we call the new vector of shocks, UT, the product between the inverse of B and epsilon T. All right. So in principle, we seem to have solved all problems because the var was born as structural, but with a simple mathematical operation, which implies that B must be invertible. I seem to have transformed my VAR into a reduced form VAR. And if there are no constraints, there is no reason to think that there are constraints because of the operation I have performed, then the reduced form VAR will be estimable by using OLS equation by equation. So we fall in the, say, nicest case that we've seen before. Before I go away, in this example, it's visible in naked eye. What does it take for the matrix B to be invertible? The matrix must be non-singular, as you will remember from the prep courses. What does it mean that the matrix is non-singular? It means that the determinant is different from 0. In the case of this matrix, the determinant is the product of the elements on the main diagonal, so 1 times 1, minus the product of the elements opposite the main diagonal, so B12 times B21. And the determinant different from 0 implies that B12 times B21 must be different from 1. Okay, so that justifies why I wrote this in the slide. Okay, so now we have the model in reduced form, but essentially I will explain in the next half an hour or so that this transformation, unfortunately, is not a resolutive one, meaning sorry, even though I've turned the structural VAR into reduced form VAR, the reduced form VAR cannot be simply addressed using OLS. So you can apply OLS, you will see, but these will leave you short of some information that you need. So at this point, I will remain mysterious, but because the rest of the slides wants to exactly make this point. So the first step is to see what happened. So what have we done by pre-multiplying everything by the inverse of B? Well, technically, we have changed the objects in the sense that gamma naught has become A naught and gamma 1 has become A1. Okay, and you will see that you can deal with this issue. But the most important thing is that we have changed the statistical nature, the statistical structure of the shocks epsilon T into new shocks UT, and these shocks UT, they are white noise, but they are correlated. So this is the proof of that for my example. So first of all, I want to write down the vector of shocks UT, UTX, UTZ, in terms of the original shocks epsilon TX, epsilon TZ, taking into account that I've gone from the epsilons to the U by pre-multiplying by the inverse of B. And these, please go and review the prep course, is the inverse of the matrix B, which essentially is the matrix of the minor principles of the transpose of the original matrix. This is called the adjunct matrix, in case you remember what it was. And you divide everything, so all the elements, by you divide by the determinant of B. And the determinant of B, as already explained 1 minute ago, is 1 minus B12 times B21. Now, that's a very simple inverse matrix, but in any case, there is no reason to memorize it because you are not in charge of memorizing the algebra in any event. But if you do the matrix times vector operation, you find that UTX is a weighted combination of epsilon TX and epsilon TZ, where the coefficients are 1 and minus B12. So it's a linear combination. And UTZ is a linear combination, a weighted combination of epsilon TZ and epsilon TX with coefficients 1 minus B21. So in principle, this is not, say, deadly news, because I think we have mentioned that one time in the past, linear combinations of white noise processes, they are themselves white noise. But let's see. So what I do next is to compute the expectation, the variances, and the covariance between UTZ and UTX to inspect whether the premultiplication by the inverse of B has in any way made their structure, more complex compared to the structure of epsilon TZ and epsilon TX. So first step, I check what is the expectation of UTX and UTZ. But it's kind of silly, meaning it's the expectation of a weighted sum of epsilon TX and epsilon TZ. You know that weighted sums of expectations, they are the expectation of the weighted sum, so you can go back and forth. And so at the end of the day, you find yourself taking the expectation of epsilon TX and epsilon TZ, and these two guys are white noise, so they have a zero expectation. So that's what happens, and you get 0 and 0. So, okay, so premultiplying by B inverse does not change the expectation of the shocks. That's good. Second, you can compute the variances. And in case you wonder, so why do you do that? Well, you just want to check that the variances of UTX and UTZ are not exploding, given what the variances of epsilon TX and epsilon TZ were, so the initial variances. And then the operation is not complex, but you have to remember two facts. So the variance of a difference is not the difference of the variances, but it is the sum of the variances of the two terms minus twice the covariance, where the minus comes from the presence of a minus sign here. Second, as always, remember that coefficients, they go outside variances, so they become coefficients in front of the variance, but when they do, they take a square. So in this case, if you square minus B12, you get plus the square of B12, which justifies this guy here. The last step is to recognize that by construction, being structural residuals, epsilon TX and epsilon TZ had zero covariance. So this quantity is in principle here, but it simplifies to 0 because that's what it is. And so the final expression that you get is this one, which is a weighted combination of the variances of epsilon TX and epsilon TZ with weights 1 and the square of B12, all right, divided by the square of the determinant, okay? But there is no reason in principle for this expression to explode. You may say, well, but if the denominator were 0, then this would explode. But it can't be, because the denominator of this ratio is actually the determinant of the B matrix. So we are able to perform the operation that we're looking at if the determinant is different from 0, which now guarantees that here, you're not divided by 0. So if the variance of the epsilons were finite and well-behaved, then also the variance of UTX will be finite and well-behaved. You can do similar algebra for UTZ, finding a similar expression. Same comment that I made now applies to the variance of UTZ. If you want to see me doing step-by-step the algebra, see the optional recording, because some of you, they like to see algebra. All right. Now, the next thing is to compute the covariance. And I really do that brute force. So I wrote down what the expressions for UTX and UTZ are. So then I take all the products. So it's like a binomial times a binomial. So you have 4 terms. And then you know the expectation of the sum is the sum of the expectations with weights. So I just went in and took the expectation. And at the end of the day, there are only 2 terms which are non-zero. So the expectation of the square of epsilon TX, which is the variance of epsilon TX, and the expectation of the square of epsilon TZ, which is the variance of epsilon TZ. So apart from the expression, which is interesting, but okay, it's just some formula, you can find the algebra of the formula in the uploaded, say, recording. In general, we will expect the covariance between UTX and UTZ not to be 0. So we started from shocks which were structural. They were not dependent on each other. And we find new shocks for the reduced form, the U's, which are actually dependent from each other. This will be a source of trouble, which I will explain in the next 10 minutes or so. So let's look at the expression. You are dividing by the square of the determinant, as always, and that will be different from 0. But the numerator has no reason to be equal to 0. So it is 0 in two situations. The first situation, which is a knife-edge situation. Knife-edge means that this happens with a probability of 0. So there is no reason to think that this will be the case in your data. But the first situation is when, even though B21 and B12 are different from 0, their sum is 0. Now, this happens when B21 divided by B12 is equal to minus sigma square z divided by sigma square x. If you look at the recording, I do the algebra of that. But there is no reason for why the ratio between B21 and B12 must be equal to the negative of the ratio between sigma square z and sigma square x. Okay. The other interesting case in which you may think that the numerator disappears and the covariance is 0 is when both B21 and B12 are equal to 0. But let's think about it. What does it mean that B12 and B21 are both equal to 0? If you go back to the original model, to the original example, when both B12 and B21 are equal to 0, it means that there are no contemporaneous effects. Or equivalently, it means that the matrix B that we have dealt with is a diagonal matrix with ones on the main diagonal. It's called an identity matrix. But you know that when you have an identity matrix, it's like having the number 1. The number 1 becomes invisible in multiplications. It's the neutral number. It does not change the result of a multiplication. And so if B becomes invisible, basically you can cross it out. The original model, the original example, is already a reduced form. So that's a case in which you have written something that you think is a structural VAR, but it's not. It's already a reduced form VAR, and so there is nothing to do. There are no problems. You can apply OLS and you will have long and happy. But it's quite a special case. That's a case in which you thought you had a problem, but you do not have any problems. So in general, if we want this to be meaningful, it will be that at least one of B12 and B21 will be different from 0. And if this happens, the numerator is different from 0, the ratio is different from 0, and the covariance is different from 0. Notice that there is a minus in front of the expression. So this probably makes you think already that there is no problem with this covariance being negative. So there is no presumption that the U's that will have to, they will have to, have a positive covariance. So I collected these thoughts at the bottom of the slide. So in general, this operation of transforming a structural VAR into a reduced form VAR has messed up a bit the resulting model, because we start from epsilon shocks, which are pure white noise and not correlated with each other, and we end up with U shocks, which on the contrary are correlated with each other, and these may be a source of problems. It's not clear yet from what I said what kind of problems. We are going to see them in a second. It's okay, but ignore the last bullet point. It's something that happens later, so no reason to comment on that. Okay, so structural VARs, because of what we just found, cannot be estimated by OLS. And the reason is that they contain contemporaneous effects. Now, to explain why OLS will fail, you have to remember, let me go back to my example because I want to use it, but you have to remember what is the assumption that is actually supporting the blue property of OLS estimators in Econometrics 1. The OLS are blue, in particular they are unbiased, which is the U of the acronym blue, when the shocks, the errors of your regression, they are independent, they are uncorrelated is enough, from the regressors. So there must be orthogonality between the regressors on the right-hand side and the shocks, the errors, for the OLS to work, to be unbiased. Now, in this case, is there a chance that epsilon tx is uncorrelated with all the regressors on the right-hand side and epsilon tz is uncorrelated with all the regressors on the right-hand side? No, because we are dealing with a VAR structural. Why? So take the first equation and think about epsilon tx. Now, it may be that epsilon tx is uncorrelated with zt minus 1 and xt minus 1. In fact, if epsilon tx is a white noise, this will be the case. The problem is what happens between, let me actually mark it for visibility, is what happens between epsilon tx and zt. So can these two guys be uncorrelated as OLS requires? No. Why? Well, if you think about zt comes from the second regression, the second equation. But in the second regression, zt is a function of xt. But xt contains epsilon tx. So when epsilon tx moves, xt moves, and xt is actually affecting zt. So in general, we should expect that zt and epsilon tx will be correlated. And if I try to apply OLS to the first equation, I will fail. So I will get estimates which are biased. Same for the second equation. So look at epsilon tz. Now, maybe epsilon tz is uncorrelated with xt minus 1 and zt minus 1. And in fact, it will be the case when epsilon tz and epsilon tx, they are joint multivariate white noise. That's okay. But let's now think about epsilon tz and xt. Can these two guys be uncorrelated? Well, that's unlikely, so no. And why? Well, xt comes from the first regression for the first equation. In the first equation, xt depends on zt, and zt contains in its belly epsilon tz, because epsilon tz is the random shock moving zt around. But if zt contains epsilon tz and zt moves xt, xt and epsilon tz are very likely to be correlated. And if they are in the second regression, if you try to estimate using OLS, you will fail. Okay, so OLS is barred from the presence of contemporaneous effects because it makes, essentially we say that it makes the residuals endogenous to the model. In fact, statistically, structural VARs, they have a second problem. They cannot be used in forecasting. So besides the estimation issue that we are going to deal with, there is also a practical issue. So think about the first regression. You're trying to forecast xt using past information. Very well. This works for xt minus 1 and zt minus 1. But what about zt? Well, to be able to forecast xt, I would have to have a forecast for zt. But the forecast for zt, where does it come from? It comes from the second equation. If I want to forecast zt, I know xt minus 1 and zt minus 1, but I do not know xt. So to forecast zt, I need to have a forecast of xt. But to have a forecast of xt, I need to have a forecast of zt. And you are in a vicious loop. You will never get out of it. So structural VAR models, in general, they cannot be used as they are to forecast the future. And especially in finance, the reason for why we deal with this type of models is entirely to produce forecasts. That's all we care for. It's not really the estimation of the coefficients. We have to go through it to make the model operational, but we care for the forecasts at the end of the day. And that's not in the right form. So this is to say that OLS cannot be directly applied to a structural VAR, and a structural VAR is not directly useful. So what we have to do is to transform the structural VAR into a reduced form VAR before using it, which is what we did. But the transformation apparently has had a cost, because in the transformation, that's here, we messed up the residuals, because now the U residuals, which are no longer the epsilon residuals, they are correlated, so they contain structure, which we are imposing on the problem. So when you have a structural VAR, so let me go back to the slide, you do have to make it operational and be able to estimate the VAR. You do have to transform it into a reduced form VAR. Now, sometimes you will not see it. So if you're working in eViews, in Stata, so this type of packages, also Python, because they have prepackaged functions, you will not be aware of that. So you write down a structural VAR, and then there will be a command or something to click that will perform the estimation. And you have the illusion, oh, I have estimated a structural VAR, and how? Well, it looks like least square, something like that, right? and it will not. So essentially what you've done is your software will have transformed the structure of VAR into reduced form, performed the estimation, and then retrieved back the estimates. The difficulty pops up when the retrieval stage comes, because in principle, I will explain why, but in principle, unless you impose restrictions on the model, you cannot simply and directly recover the estimates of the structural VAR from the reduced form estimates that you get from OLS, by OLS, or by simple methods in any event. And this difficulty in going back and forth between the OLS estimates of the reduced form VAR and the original, the estimates of the original coefficients in the structural VAR as a name is called the identifiability failure or identifiability issue that structural VARs present. Now, I've got two ways to explain that. So the important is that one goes through. First way to explain why you are facing identification problem when you apply OLS to the reduced form, but you care for the structural VAR, is just to look at the formula here for the covariance between UTX and UTZ, the formula that we have seen together 10 minutes ago. This formula has one feature. When you will be on the data, so inside your software package, covariance UTX, UTZ will be one number. This will be replaced by a sample estimate of the covariance, right? So it will become a number. It's an easy function in Excel, in fact. So you will have a number on the left-hand side, but this number will be equated to a formula in which in the formula you will have potentially other numbers, sigma square x, sigma square z. Well, these may be numbers, but there are also coefficients. And there are two coefficients on the right-hand side, B12 and B21, and they're both present together, and they're multiplied one with each other, if you see here. So it means that you can get the same number on the left-hand side with an infinity of possible combinations of B12 and B21 on the right-hand side because of the very structure with which they enter, which comes from the determinant. So when this happens, it's like if you want to determine two coefficients, B12 and B21, just with one equation. And in general, a system of one equation with two unknown, it cannot be solved. It leaves you in indeterminate situation, which means that you have a lack of identifiability of the coefficients B12 and B21. Now, that's the simplest way to explain it, okay? So the logical way. So what is the issue of identifiability? The fact that even if you do correctly the estimation by OLS of the reduced form, it's unlikely that you will be able to jump back to know all the coefficients that populated the original structural model. Now, there is another way to explain that. Some of you may like this one better, but it's, sorry, too much, but it's completely equivalent. It's here. So if you write down the original example and you count the number of parameters which appear in the original structural VARs and the number of parameters which appear in the transformed reduced form VAR, which comes from the structural VAR, you will notice the existence of one imbalance, in the sense that there are many more parameters in the original model than there are parameters that you can estimate on the data in the final reduced form model. And this imbalance is the cause of the identification issue. Or if you want, the imbalance is caused by the new nature of the shocks U, which now contain a covariance, but this covariance, sadly, is a function of both B12 and B21, so all the elements inside the matrix B. So let's do it. It's not difficult. So first, consider the original model, which is the structural VAR. It's quicker to actually look at the regressions, at the equations, not in matrix formats. So how many parameters do we have in the first equation? So 1, gamma 1, 0, 2, B12, 3, gamma 1, 1, 4, gamma 1, 2. And remember, there is one inside epsilon tx, because epsilon tx is a variance which needs to be estimated. So 5 in the first equation. In the second equation, same thing. So gamma 2, 0, B21, gamma 2, 1, gamma 2, 2, and the variance of epsilon tz called sigma square z. So 5 plus 5 is equal to total of 10. So in principle, I expect to be able to do things to this model such that using the data which I have available, I will be able to estimate 10 parameters. But if I transform, as I think it's a good idea to, if I transform my structural VAR model into a reduced form model, sadly, I seem to lose one parameter in the sense that you create this situation of lack of identification. And let's see why. Well, this is a transform model in reduced form. There are two elements inside A naught, so two constant coefficients. There are four elements inside A1. A1 is a matrix 2 by 2 with the coefficients A11, A12, A21, A22, so it's 4. And then finally, I've got UT. UT has a covariance matrix. And in a covariance matrix, even though it's a 2 by 2 matrix, there are only 3 elements. The reason is that covariance matrices, they are symmetric. So there are 2 variances and 1 covariance, which is repeated above and below the main diagonal, 3. So 2 plus 4, 6 plus 3, 9. So it seems that I can just recover 9 parameters from the reduced form model, which is less than the 10 parameters which populated the original structural VAR model. One way to see that, so now I'll just say it, but you will find the slide soon in a few minutes, which actually exactly has that, is to say that when you try to estimate the original parameters of a structural VAR going through the parameters of reduced form VAR, it's like facing a system of equations in which you have too few equations given the number of unknowns that you want to determine, that you want to find out. And in general, as you know, when a system of equations has too few equations compared to the number of things that you want to pin down, you will not be able to solve it, in the sense that you will have probably an infinity of solutions. It's an indeterminate system of equations, we say. Now, indeterminacy, in the case of econometrics, is called lack of identification of some of the original structural VAR coefficients. Now, just logically, if I give a problem in which you have a system of equations with too few equations and too many unknowns, what is the reaction? So first reaction, well, you try it, you can't, and you can characterize the infinity of solutions if you think about your studies in math, but then you surrender, right? So in this case, that's not a good strategy. It means that you go back to your boss, say, oh, look, I can't. Right? But we knew already that you couldn't. Second solution, well, if you have a system of equations with too few equations, add equations, right? So you add other restrictions written with equality, which helps you to pin down the unknown that you're looking for, in this case, the estimates of the parameters. Some people do that. So it's one valid way to solve the identification issues of structural VARs, to create new restrictions, which do not come from the pure econometrics. They must come from somewhere else. So they must be common sense restrictions, like, I don't know, something like B12 is equal to 4 times B21. That's okay. Or they can come from theory. Now, we are in a finance course, so not always we have excellent theory about the stuff that we are modeling. We just want to forecast, really. But if you switch a bit to macro, or if you look at interest rates, which is also a finance topic, you will find many sources in models of potential restrictions that you want to impose, which are extra equations. In fact, I don't know if it's written anywhere in the slides. There can be situations in which you end up imposing too many restrictions, which is too many equations. In this case, not only you solve the problem of identification, but you will face VARs which are over-identified. So there is lots of constraints, like a straitjacket, given the unknowns that you have available. That's okay. These restrictions can be rejected or not, they can be valid or not, but it's something we can deal with. Finally, if I give a system with too few equations and too many unknowns, what is the other solution if you do not want to increase the number of equations? The opposite, which is to kill some of the unknowns. You just cross them out. You set them to some number, you set them to 0, so you don't want to deal with them, essentially, okay? And this is the favorite solution in this case, although it seems to be very brutal. So the favorite way in which structural VARs are identified, and therefore they become estimable, they become manageable, because they become equivalent to reduced form VARs, is by killing an appropriate number of coefficients. Removing is the elegant word, an appropriate number of coefficients. Now, the thing I want to impress on you, please, is that it doesn't matter which coefficients you remove. The important is that after you remove them, you remove a sufficient number of them. If you try to solve again the system of equations, now you are able to, because you lost the unknowns, the excessive unknowns that before you were not able to solve. But there is, so you can impose restrictions on the covariance matrix of the U's, you can impose restrictions on gamma 0, you can impose restrictions on gamma 1, you can impose restrictions on, no, that's it, gamma 0, gamma 1, and you can impose a restriction on B, right, that's what I was forgetting. Now, historically, there is one favorite target for such removal of coefficients, and the target is quite natural, is the B matrix. Why do I say that the target is natural? Because it's related to one of the explanations I gave you, one of the intuitive explanations. The issue of identification comes from this equation, from the fact that you got a number coming from the data on the left-hand side when you do the estimation, but you got two coefficients on the right-hand side, and you're not able to disentangle the effect of the two coefficients. So solution is, well, kill one of them. So kill either B12 or B21, where to kill means to set to 0, but also possibly to set to a constant. But since people do not have a clue about which constant usually, it's typical to remove coefficients by setting them to 0. Now, formally, we say that most of the time structural VARs are identified by making the B matrix a triangular matrix. And this style of identification, which is not the only one, but it's a very common one, is called either Cholesky factorization, I will explain why, or it's called Sims triangularization identification. So what does it mean to take the matrix B and kill a portion of it? You see that in the next slide. So here I have identified my structural VAR, making OLS estimation possible by setting B to 1, so what used to be here, by setting the coefficient B to 1 equal to 0. And if I do, what happens is that in the second equation, in the second regression, the coefficient B to 1 is no longer there. And therefore, the B to 1 times xt, which used to be on the right-hand side of the second regression, has disappeared. And so this creates an imbalance, an asymmetry between the first regression and the second regression. The first regression says that xt keeps being contemporaneously influenced by zt with a coefficient b12 that we will be able now to estimate using OLS. But the second equation says that zt instead does not contemporaneously depend on xt. Now, let's stop immediately and think about the intuitive meaning. So by doing this, I have solved a mathematical problem, because now, let me go back. If you kill the coefficient b to 1, automatically in the structural VAR, the number of coefficients that you have is no longer 10, it becomes 9. And the number of coefficients that you have in the reduced form VAR is 9. So with 9 coefficients in both models, you will be able, possibly, probably, you are guaranteed in this case, to find a solution and so to identify the structural VAR. However, we have changed the meaning of the system. And in particular, we have created sort of an ordering of importance between xt and zt. We have created an ordering of importance between the two variables. In what sense? Well, now we are in a situation in which zt seems to be primitive compared to xt, more important than xt. Why? Because zt is just hit by its own shocks, epsilon tz, and the effects of the legs of xt and zt. So it's kind of a bit relatively autonomous compared to xt, because zt moves around contemporaneously today just because of its own shocks, not the shocks of epsilon tx. Xt, on the contrary, is dependent on its own shocks, epsilon tx, but also the epsilon tz shocks. And this is visible from the presence of b12 times zt. If there is a shock epsilon tz on zt, zt changes, but the presence of zt on the right-hand side of the first equation also makes xt change. So by killing one coefficient inside the B matrix, we have done something which is mathematically very simple, I would say. But at the same time, we have introduced a sort of arbitrariness in the way in which we write down and we see our own structural VAR, which is a bit less structural than it was before, because now it's no longer true that xt and zt are on the same level. Zt has gone before and above xt. So xt depends on zt, zt does not depend on xt. And that's also the sense in which we tend to think about this as a triangularization, because we make the very structure of the VAR model that we are facing unbalanced if you look at that, right? It's no longer so symmetric as it used to be originally. Now, natural question is, Massimo, okay, I see B21 is gone and this simplifies matters, but why B21? Why not B12? And you're right. So the problem with triangularizations, in general, the problem with removing coefficients to reach identification is that their removal is often not supported by any deep insights into the data, any theory, for instance. You're just removing things because if you do not remove them, you're not able to estimate the model and handle the model. And so there are two thoughts. First, you have to be, actually three thoughts. First, you have to be transparent about how you have identified your structural VAR. And when we will be in e-views soon, next week, I will show you that everything can be done in a very clear and transparent manner. So you have to report it. Second, probably you will have to, in some situations, estimate your model, trying different sorts of identification. So trying to remove different parameters and see whether the conclusions you care for, like your portfolio allocation, your risk management applications, they depend a lot or not from which assumption you make. And third, because choosing which elements of B you remove corresponds to creating a sorting and ordering of the variables, so which are more primitive and which are less primitive, which depend a lot on the others, which depend less on the others, you should also address the problem in this way. So in front of a VAR, you should ask yourself, well, now I need to identify it, and which are the variables that are more likely to move autonomously, not really reflecting much of what happens in the others, and which are, on the contrary, the variables which I care for, but poor guys, they also reflect contemporaneously everything that is happening in the rest of the system and the rest of the VAR. So there are three consequences of this style of work. Now, because we have seen that the covariance matrix of the use comes from the covariance matrix of the epsilon, but it must discount, sorry, I received something that interrupted. But we must discount the fact that we have to pre-multiply by the inverse of B. Some people prefer to see the triangularizations not really as restrictions on the matrix B, as I've sold them to you, and I think it's the most natural to look at them, but as restrictions that you are imposing on the covariance matrix of the use, okay? And so essentially, if you can look at the book, if you want to know exactly the story mathematically, but the idea is that to triangularize a VAR is the same as imposing a Cholesky structure on the covariance matrix of the U. They are equivalent. But I prefer, and that's the same in e-views, for instance, to think about the contemporaneous matrix B instead of thinking about the covariance matrix, although they are the same things. But do not be surprised if you read around, like even in report by banks, in the quant desk of banks, that they have identified the VAR through Cholesky triangularization, as if they're talking about the covariance matrix. They're really talking about the B matrix. Okay. Now, if you look at the optional posted note, the recording, I work out the full algebra Y. Killing one of the two coefficients inside B works. And essentially, I show you that after you remove the coefficient B21, what happens is that in the reduced form, you have 9 parameters, and these create 9 equations, so a system of 9 equations in which you can find 9 unknowns, and the unknowns are the 9 original coefficients from the structural VAR. Now, so the equations are here. And I know that they don't look like a nice system of equations, but you can rewrite it to look like a system of equations, and it looks less scary. Now, some of the equations they are stupid equations. They are really assignments. They are identities. Like, look at this one. It's a trivial equation because you have identity between one coefficient A02 in the reduced form and the original gamma 20 coefficient in the structural VAR. And the same happens here, the same happens here, the same happens here. So you have like 4 of them which are like assignments. There is a 5th one which is kind of trivial. That's a silly linear equation which you can use to determine B12. And you see what is happening. The source of the problem was really the equation about the covariance between the U's. After you set B1 equal to 0, such equation actually simplifies to become very simple. Now, there are a few more equations, the remaining 4 equations, 1, 2, 3, and 4, which instead require that you work with paper and pencil. It's not very hard, but there will be some calculations to be done. Now, in reality, you have to do nothing. The machine, the software you're using, does very quickly, in a matter of a fraction of a second, all these calculations for you. So using linear algebra, using matrices and vectors, by the way. Now, every time you take your structural VAR and you impose a number of restrictions, either adding equations or especially removing parameters, which is just enough to be able to recover all the coefficients from the structural VAR, you say that the structural VAR has been exactly identified. Now, this holds in general. In my example, it's a VAR1, but I will tell you more in a second, but it could be any VAR. So when you have exact number of equations equal to exact number of structural coefficients, then you talk about exact identification. In finance, we aim for exact identification. So we want to estimate this beast, okay, and make it operational and be able to forecast, okay, very pragmatically. Now, if you study macro, in macroeconomics, they are first in the business of adding equations, not really just removing coefficients. So they mix the two. They add some equations and they remove some coefficients first. And second, sometimes they have theories, models, which are rich enough that they can actually add many more equations and remove lots of coefficients, more than needed. So they may end up having, in this case, more equations than unknowns. In this case, the VAR is said to be over-identified. And the advantage of over-identification is that it allows you, by testing the VAR, to test the underlying model, the theory that impose the restrictions. But we will not do that. So I just wanted to mention that. Okay, in general, so this was an example, okay, with 2 variables. The simplest possible example, n equal to 2, p equal to 1. In general, how many restrictions do we have to impose? So how many equations do you have to add, or how many parameters, coefficients of the structural VAR do you have to remove? Well, the formula is very simple in the sense that all it takes is that you make the B matrix, the matrix of contemporaneous effects, a triangular matrix. So you either have to kill everything below the main diagonal or everything, all the coefficients above the main diagonal. And by doing that, you are imposing a number of restrictions, a number of removals, which is equal to n squared minus n divided by 2. Because the number of elements either above the main diagonal or below the main diagonal of an n by n matrix, and B is such, is equal to n squared minus n divided by 2. So it's always like that. Okay, so you can write down all the examples you want. At the end of the day, you will discover that unless you make the B matrix triangular, you're not removing enough parameters to achieve identification. In our case, we had 2 variables because it was a simple example. So if you put 2 inside the formula, so the square root of 2 is 4, minus 2 is 2, 2 divided by 2 is equal to 1. So you just needed 1 restriction to achieve exact identification, which is what happens, and I actually showed you, especially if you look at the recording, that this is the case. But if I give you big VAR, then with big N, I mean, then the number of restrictions that you will have to impose is quite extensive because there will be many, as you can see. 2 comments. So notice that nowhere here in the formulas there is P. So it appears here, but just to indicate the VAR. So the number of legs on the right-hand side of the VAR does not really interfere with the practice of identifying the VAR. So of imposing restrictions. So the number of restrictions required for the VAR 1 are the same as the number of restrictions required for the VAR 15. Okay. Second comment, I already said that, but let me emphasize it. Now, you're not forced just to work with the B matrix and essentially create an ordering of the variables. There are people who are agnostic about it, so they mix and match different kinds of restrictions, or even they kill some coefficients in the B matrix, but also outside the B matrix, and they also create additional equations. So they add equations, so they add restrictions of a different kind. Now, on the mix and match, it is true that by setting some of the coefficients in gamma 0 or gamma 1 matrix equal to 0, you could achieve the point. So by acting on the gammas, you can actually identify the model, but you need to check that. So it's not automatic. So as long as you're acting on the B matrix, you're guaranteed the result. When you're acting on gamma 0, gamma 1, then it depends. It depends on whether you are intervening on the right equations or not. So your software will have to do those calculations for you as well to check identification. Okay. Now, this is something that we discussed already, but let me emphasize that if I give a big N, there are many possible ways in which you can impose the triangularization. Now, it doesn't look like, if I give a B matrix and you look at that, you're like, Prof, either I kill everything below the main diagonal or everything above the main diagonal if it has to be eventually a triangular matrix. This is not the case, really, because the important is that what you set to 0, what you set to a number, is with reference to n squared minus n divided by 2 elements of the B matrix. So in principle, you can get a B matrix and put zeros, enough zeros around, and at the end it will look like Gruyere, you know, the cheese with holes, okay? And after you do that, you're like, well, okay, now I have imposed the restrictions, but this is not triangular. It's like Gruyere. Now, remember that, however, for any B matrix, it's like when you do the Kublik's cube, the Kublik cube, you can always reorder the row of the matrix such that all these zeros, and reorder the columns of the matrix, and consequently the row of the matrix, such that all the zeros that you find, they are put in a place such that at the end you will have a triangular matrix. Why can you reorder the rows and columns of the matrix? Because in a VAR, the way you stack the variables is completely arbitrary. Like in my case, I had x and z. Why x above and z below? I mean, is it the same VAR if I first write z and then I write x? Of course it is. So the order in which the variables appear is usually alphabetical if you look around the literature, if you look around books. There is no effect of putting a variable first or last or in the middle. And so you're free to change the order with which the variables come, and to show that if you impose enough zeros, enough restrictions inside the matrix, the B matrix must always be such that it can be rewritten as a triangular matrix. So the general point we made is important. Problem. Well, this implies that there are many possible ways. It's like a factorial, say, computation, a combinatorics problem, in which you can identify your model if n is large, and you're right. So one of the big difficulties of the Cholesky identification, of the recursive triangularization type of identification, is that there are many possibilities, and in principle, you should explore all of them to be sure that your results are not entirely driven by what you pick. But we will have a chance to speak about it again in the next class, and then you will see what eViews has about it. Okay, now, so let's move forward. And this was a big issue if you want to use structural VARs, which in fact happens, but it's not dominance, also because people want to stay away from all these problems, but you need to be aware of it in case you want to have contemporaneous effects. Now, most of what I said about VARs and identification and so forth holds if you're dealing with stationary VARs. What is the definition of stationarity in the case of the VARs is the same as we saw together for autoregressive processes. So there is really no change. in the way you should go about them. And so let me briefly review it. Essentially, a stationary VAR is one in which the first two moments, they exist and they are finite, although the moments are now very complicated, but it's the same business as before. And so they are not a function of time. And the fact that the VAR is stationary allows you to fish from the past, so to use past data, to learn about the structure of the connections of the variables, so to estimate the VAR, and to be able to forecast the future. And if a VAR is stationary, under some conditions, which usually are ignored, it is also a linear model. And you know that under linearity, there is a collapse of weak and strong stationarity. So they become the same. And so usually VARs, they are analyzed under the profile of overall stationarity. So we just say stationary, we do not specify whether it is weak or strong, meaning that probably they will be the same. Okay, so effectively that's what happens. Also, as in the case of ARMA models, you know that if an ARMA model is stationary, then Walt's theorem applies. What is Walt's theorem? Well, it says that any ARMA model, including an AR model, can be rewritten as an infinite moving average model in which the coefficients of the moving average, they are not explosive. They do not blow up in your face. And the same applies here. So when you have a VAR which is stationary, the Walt's theorem applies to the multivariate case. And see the slide, YT can be written as a VAR, but also equivalently in the way that you see here. So it's a constant mu, which happens to be the same as the unconditional expectation of YT, plus an infinite sum of past shocks, and there is a current shock as well. And the past shocks, they are vector shocks in this case. The ut minus j, they're vectors, and they're preceded by coefficients which are called theta j, theta I don't know, it's I really, theta I. And this theta I can be shown to be a function of the original parameters, of the original VAR coefficients. If you look at the book, there is one case in which you have the development done in front of your eyes. So it's like an example of algebra, and that's the case of VAR1. Now, the truth is that the algebra for VARPs is very intricate in the sense that these theta I coefficients, these matrices, they are complex matrices of sum of products and powers of the matrices in the original VAR. So the A1, A2, AP matrices. So it gets nasty, ugly very quickly. And we're talking about powers of matrices. We're talking about products of matrices, no longer, it's not scalar coefficients, it's not numbers. But in the case of VAR1, then it's fairly simple. So the Walt's decomposition that you see up there becomes the one that you see in the middle of the slide. And the theta I, these matrices, they are just powers of the A1 matrix. A1, just A1 because it's a VAR1. Before there is any confusion, notice that the power of a matrix is not the matrix of the powers, please, okay? The power of a matrix is the matrix multiplied by itself, if you want, pos multiplied by itself, I times. So A1 to the power 0 is by convention the identity matrix, is a convention. A1 to the power 1 is A1. A1 square is not the square of the elements, is A1 times A1. And you have to do the product, is a matrix which multiplies itself. And you have to use software to do it. A1 cube is A1 times A1 times A1, and so on. Okay. So computers are very good at handling that because they run products of matrices quite effectively. But otherwise, in a world of paper and pencil, it would be very painful to take powers, of course. Okay. Now, the algebra of the Walt's theorem works in the same way that we have seen in the case of ARMA models. So essentially, you can start from your VAR, and by recursive backward substitution, you can rewrite it going backwards, going backwards, going backwards. And as you go backwards, you have an increasing number of MA-type coefficients, so these guys here, and this number goes to infinity. And you have a leg of YT, say YT minus H, where H goes to infinity. So you have an increasingly distant leg of Y, which appears on the right-hand side. Now, that increasingly distant copy of Y, YT minus H, is preceded by coefficients, by some complex coefficients. And that coefficient is a sum of products and powers of the matrices in the original VAR. Now, for sums of products and powers to disappear, so that you have the Waltz theorem, so you have this representation, you need these matrices to be small, meaning when you take matrices which are very small and you take products of them, you take powers of them, they become even smaller. Okay. Now, in the case of a number, we have a clear feeling for what does it mean that a number is small, such that if you take products of powers, the number, the product of the power gets smaller and smaller. You need numbers which are less than 1 in absolute value. So 1 is the threshold below which numbers are considered small in products and powers. In the case of matrices, however, we cannot compare them to 1. So it must be something else. It must be something in the deep fabric of the matrix, which basically rules whether these are sufficiently small or not to react in the right way when they are involved into the development of the Waltz theorem. Now, it turns out that the behavior of matrices in the face of powers or products is ruled by the eigenvalues of matrices. The eigenvalues are special numbers. They're like indicators of the behavior of matrices, which come out from solving a system of equations of this type. They're called determinant system of equations. And many of you will remember these because that's the system that you have to write down and solve to find the eigenvalues of the A1 matrix. Now, there are two ways to go about it. So stationarity will be ensured because these powers and products I was talking about, they disappear in two cases. And these are equivalent. So it's just two different ways to state the same property. First case, when all the eigenvalues of the matrix is involved, in this case of the A1 matrix, they are less than 1 in module. Module is very important because some of these eigenvalues will be complex eigenvalues, and you know that you cannot talk about the absolute value of a complex number. You have to talk about module. Now, do we care? Do we have to do it? No. But when you will have a VAR, you will see in e-views soon, next week, it will print out the eigenvalues, and some of them, they will be strange. They will be like 2 numbers instead of 1. Those are the complex ones. The equivalent way to say it is to say that once you write down and solve the determinant system of equations, which is this thing that you see here, the system of equations will have roots called characteristic roots, okay, as they were called in ARMA models. If all the characteristic roots in absolute value, in module to be precise, they are in excess of 1, then your VAR is stationary. Now, also in this case, something that we did in the past applies. Technically, you should talk about stability of the VAR, but practically for all purposes, unless of pathological cases, stability and stationarity of the VAR, they are equivalent. So we treat them as if they are the same. When a VAR is stationary, so when these conditions are satisfied, then you have Waltz theorem working for you. And so you can trust this way of representing things. Why is it important? You will see. Next lecture will be about exploiting this representation to do things with VAR, which will confess about the connections among variables, so the way they move or they fail to move together. Okay, now, since we are talking about stationarity, it's natural to talk about the moments of the VAR, conditional and unconditional moments. So I start with VAR1, which is the case for which I think you find the algebra in the book. The algebra for VRP, some of it is easy, okay, no problem. Some of it is very complex, and so it's for advanced treatment. These are the first 2 moments of a VAR1. So the mean, which is actually a vector of means, the unconditional expectation, and the covariance matrix. The covariance matrix of a vector of random variables, as you know, includes the variances of the main diagonal and the covariances outside the main diagonal. Why do you want to do the calculation? If a VAR is stationary, the moments should not explode. There should be no reason for them to blow up. And second, they should not be a function of time. So there should be nothing index time on the right-hand side. Let's look at expressions. There is proofs of that, so you can see the book. I don't know if I have some note with algebra on that. I will see whether I can fish something out and post it, but it's not required, of course. The mean looks like the expression that we've seen in the past. Remember that the mean, the unconditional mean of an autoregressive process is phi naught divided by 1 minus phi 1. We saw that. Here we have the same. So phi naught is no longer there. It's a vector of coefficients called a naught. But okay. And you cannot divide by something, right? Because you should divide by matrices in counts. But instead of dividing by matrices, you can actually pre-multiply by the inverse of stuff, which is what you do. You pre-multiply by something which is the inverse of in minus a1, which kind of looks like, it feels like 1 minus phi1 that you normally divide for in the case of the AR model, but this is a VAR model, this is a vector model. All right. The story behind the covariance matrix is a bit complex because you end up evaluating this object here. And this object has one peculiarity. It's an infinite sum of powers of matrices. So that's really a place in which the eigenvalue story kicks in. Because if the eigenvalues are badly behaved, these a1 to the I power, when I goes to infinity, they will blow up. And so the covariance will not exist. So stationarity really kicks at this point. Now, there is no, there is a formula, but it's ugly as hell, even in the case of the VIR1 to look at for the covariance matrix of YT. But this formula becomes digestible, and it is the one that you see in the slide. If instead of thinking about the covariance matrix of YT, you think about the vec of the covariance matrix. What is the vec? Is when you take a matrix and instead of representing that matrix, you actually stack the columns of the matrix in a long vector. So you take your matrix, you take the first column and you write it, fine. You take the second column and you write it below the first column. You take the third column, you write it below the second column. You take the fourth column, you write it below the third column. And you keep going until you exhaust all the columns of the matrix. So it becomes a long vector in which you have n square elements in the rows, and you just have one column because it's a column vector. Now, if you're ready to represent things in this weird way, then there is a formula that can actually fit a few centimeters only instead of taking the full page for the covariance matrix, and that's the one that you see here. Now, that's kind of nice because if you think about AR1 models, the variance, the unconditional variance was sigma square epsilon divided by 1 minus the square of phi1. And here you get something similar, really, because instead of sigma square epsilon, a number, you get the vec of sigma u, but sigma u is sigma square of the residuals for this case. And instead of dividing by 1 minus phi1 square, you have a pre-multiplication by the inverse of, but it's like dividing the identity matrix, so kind of 1, minus the square of something, the square of the A1 matrix. Now, the square, however, cannot be dealt as a usual square, and it becomes a Kronecker product. I don't know if it was in the prep course, but not so important, right? This happens inside the belly of software. But what is a Kronecker product? So in this case, it's the Kronecker product of A1 by itself, by the way. So it means the first element of the matrix A1, so A11, times the full A1 matrix. Then the second element of the first row of the matrix A1, so A12, times the full A1 matrix. A13 times the full A1 matrix. A14 times the full A1 matrix. And then you go down, A21 times the full A1 matrix, and so on. Okay, so it's a massive, giant matrix, which will be n squared times n squared. So massive, okay? But you need it to be able to perform this type of operation that you see there. Now, in the end, you will see an example in 5 minutes, less. We care for the numbers that come out, but the type of operations that our softwares have to do to deliver those numbers they start being non-trivial at this level. Okay, now these, the ones that you saw, they are the unconditional moments. And so under some conditions, which are equivalent to conditions of the eigenvalues of the matrix A1, they will exist, and they do not depend on time. Okay, what are the conditional moments? Well, conditional moments are when the expectation of the covariance matrix, they are a function of the information set. Usually, they tend to be a function of the most recent available information. And the expressions for the conditional moments are A, silly, because they just come from the VAR model when you kill the shocks, because the shocks are white noise, they have zero mean. And so, for instance, the conditional mean expression is given by this one, which is just your VAR model without the shock. And however, if you compare the, let me change color. If you compare the conditional mean with the unconditional mean, they got nothing to do with each other. I mean, the ingredients are the same, but they are combined in ways which are very different. So the unconditional mean is kind of non-linear and heavily dependent on the eigenvalue things that I told you before. The conditional mean is just a linear function. There is a surprise when it comes to the covariance matrix. So the unconditional covariance matrix, to be precise, the vec of the unconditional covariance matrix is this formula that we've seen already together, quite right. Guys, can you hear me? For a moment, things went weird. Now, yes. Ricardo, Luca, for how long was I gone? Just a few seconds as I perceived it, or longer? 5 seconds. 5 seconds is okay. Okay, thank you, guys. Sorry. I think I was saying that, yes, in the unconditional variance, we have these complex expressions that you saw already. Now, if you do the algebra, which is simply to recognize that the variance of something that you know is zero, right? So this guy must be zero here. Then the formula for the conditional covariance matrix, in the case of VARs, is actually silly. It is this one. So it is much simpler than the formula that you find above. You will see one example in a second, which really emphasizes this difference. Told you. Okay, here is the example. So I took the data that I've used already to motivate the cross-serial correlations, and it's a bivariate VAR, two variables, with 1 month interest rates and 10-year interest rates for the US. I don't remember when they start, honestly, from the 80s probably, but it's not important. And first, I have estimated the VAR by OLS. Reason is that it's a reduced form VAR. And you know that, you see that, because there is nothing in front of YT on the left-hand side. There is no B matrix. When the B matrix is not there, it means that it's identity matrix, so we do not have to worry about it. It's already identified. Fine. And these are the estimates, all right? In eViews, you will see that it takes like half a second to do the estimation, probably less. And the numbers in parentheses, they are t-stats. I did that on purpose because there are papers, there are reports, there is stuff that you will see in which folks are reporting not p-values, but t-stats. That's a bad idea in my view. So I always report p-value, but I mean, just as an exception, just to train you to the fact that you could find something else out there in the world, here are t-stats, but okay. So the way you use them is the usual one, right? So if in absolute value they are above 2, then there is statistical significance. If they are below 2, then not. So maybe there is something to say, to worry about. Okay. Fine. This one is the estimate of the covariance matrix of the residuals. In this case, we call them U because it's a reduced form. So this could be a structural model that has already been turned into reduced form. We don't know, so we don't care. Since we don't know, we do not have to worry about it. And you see that the numbers that you get are very small. We're talking about something like 4 basis points, 1 basis point. So very, very small numbers, right? And why so? Okay, let's make a comment, because otherwise this number may look strange. The reason for this is that interest rates, they are highly autoregressive. They are close to be unit roots, by the way, so they are very, very serially correlated, so that when you place some legs of themselves and other interest rates on the right-hand side, they have very high R-squares. The R-squares are so high that the residual variances, so this is what we are looking at, they are very small. So we are talking about R-squares of 99%, 99.5%, okay? Now, do not get excited. It's a VAR. It's an extension of an autoregressive model. So the fact that you can explain a phenomenon with its past is better than nothing, but it's not something to really be happy about. So same comment which I usually make. Then I took the numbers, and I use them, and it takes a computer to do it, so no paper and pencil, I think, to compute the unconditional mean and to compute the unconditional covariance matrix, which I rewrote already as a matrix just for convenience. And the unconditional mean is 0.56 per year and 2.84. And the unconditional covariance is this one, 4.7, 2.9, and 2.7. Now, the first thing that I want to stress is that this unconditional covariance matrix is very different from the conditional one, from the sigma hat u that you saw before. And because we are talking about numbers which are like 100 times bigger compared to the original covariance, sorry, to the residual covariance matrix. How can it be? Well, the reason, if you think about it, it comes from an AR model. So if I take a very small sigma square and I divide by 1 minus the square of a number very close to 1, so phi1 square very close to 1, so phi1 square is a number close to 1, I'm taking sigma square epsilon, which can be very small, and divide it by essentially 0. So I blow it up by 100 times, by 1,000 times, which is exactly what happens here, although that's a VAR. So what you're blowing up for, it's really by using this type of formula that you've seen, as ugly as it is, but my software has done the calculation for me. At the bottom, there is an example of a conditional moment, and that's the conditional mean taken on September 30th, 2016, whatever. You just plug in the number and you do the calculations. But what I wanted to stress is that these conditional mean, let me actually, okay, this one is very different from this one. But you're not surprised, right? Because you know that the conditional moments can drift away from the unconditional one, even vastly, provided that they eventually go back, which is the definition of stationarity. Okay, how do these things extend to the general case of a VARP? Okay, when you have more than one leg. They do. It's just painful algebra. The proofs, they work in the same way, they're just harder to do. So the unconditional mean has a similar structure, and that's the case in which the proof can be done not too painfully. So instead of pre-multiplying by in minus a1 inverse, you have in minus a1 minus a2 dot 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 minus ap inverse. Okay, that's simple. The conditional means, they are just an extension of what we saw. So instead of taking into account of one leg of y, you have to take into account of many legs, but I see no difference. The real problem comes with the unconditional covariance matrix, in the sense that there is no formula like this one. Maybe there is, and when I opened the page of that book years ago, obviously, I must have closed it immediately because it took a few pages. So there is nothing so simple. And the best way in which people compute the covariance, unconditional covariance matrix of the VRP models is by doing something which is equivalent to writing and solving the Yule-Walker equations. So it's a bit hard, but we don't care, right? Because anyway, computers do that for us nowadays. Stationarity is defined in the same way, but you're no longer talking about the eigenvalues of a matrix. So you can either build a super matrix, it's called companion matrix, which is actually a matrix in which you will find inside the matrix matrices, because A1, A2, blah, 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 AP, they have to enter in special ways that matrix. It's a huge matrix, and at that point, you will be able to study the eigenvalues of that. This is doable, you find it in the textbooks, but it's not the way in which it works in practice. In practice, what you do is to write down the determinant system of equations, which is defined in the usual way, so there is not much change compared to before. Solve it, so find the roots, the solutions, and check that the roots, they are all more than one, in excess of one in module, which is the usual thing that you do. So practically, this is the way your computer will speak about stationarity. Now, wow, okay, I have a couple of minutes, right? So, all right, so let me start transitioning to the next thing that we'll talk about, which is the choice of P, the choice of VAR model. Now, you remember from ALMA models that choosing P and Q is always critical. In the case of VAR, it's super critical. Reason, if you're not careful and you specify a P which is too large in the case of a VAR, you will end up having a model which is massive, which is too big. The reason is that if you do the counting of the number of parameters in a VAR-P model with n equations, with n variables, the number of parameters that you have is equal to n, the constant, n squared times p, because there are p different A matrices, so A1, A2, blah, 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 AP, each of them has n squared elements, so you multiply by p, and then you have the elements of the covariance matrix, which are 1/2 times n plus 1. And right, with your computer, with your calculator, if you plug in some values for n which are ambitious, say 100, then it's a massive amount of parameters. So in the case of VARs, it's a legend, this one. It's easy to find yourself estimating more parameters than the number of data points that you have, which makes no sense. You shouldn't do it, okay? So when it happens, you should resist the temptation of doing that. Why can it happen? So you would expect a decent software to stop you from doing that, but it doesn't. Why? Because we know that under some conditions, if your VAR is a reduced form and unrestricted, you can estimate the VAR equation by OLS. So you may end up estimating with 1,000 data points a VAR which has 2,000 parameters, and you do not even realize it. And when you do it, I don't know if I would put any faith, any trust in the coefficients that you are estimating, obviously. So we have to be extremely conservative and careful when it comes to the specification of the number of legs that you have in a VAR, all right? And so next time, so there is a danger of overfitting. Next time, I will tell you what procedures are in place to make an appropriate choice of P. And essentially, you will see that some of the procedures, they are new, quote unquote, in the sense that they are application of the likelihood ratio test principle that I think we have reviewed quickly, but we have reviewed in the prep course. And there will be once more usage of information criteria, as we did in the case of ARMA models. But this is the matter for tomorrow's class. Okay, guys, thank you for being here, being back also. But the numbers are what they are. If you have questions, I will stick around for a couple of minutes to take them, and otherwise I'll see you tomorrow. Ciao. And I will stop the recording.